I think it's going. Yes, it is going. Okay, so let's do the MorrisLeCar type 2 excitability. And let me demonstrate the new form of bistability. Just speak up if you want me to make my numbers bigger or smaller. I'm trying to show you this. Okay, so here is the MorrisLeCar system with applied current of 0, nothing is happening. We're at rest. So this is the one where we have the unique bistability at the current of 90. Nothing's happening here. So let's introduce a current pulse and try and knock it off of its resting state. So what I'm going to do is I'm going to deal with the one that's a little bit easier. That's the first current pulse. I'm going to give a 5 millisecond current pulse between 200 and 205, so about right here, and try and knock it off of its stable state. So I'll try something really small, like maybe 25 picoamps. Boom. So did you see how that worked? See the inflection here? That current pulse turned on at 200, and it kicked it off that resting state, and it made it cross the separatrix of the unstable periodic orbit, and it went into its oscillations, and now it stays there virtually forever. It would never leave that state. Good with that? So how about the second one? So I did the heavy lifting for you, and I mucked around until I found something that worked. And what seems to work is to turn it back on at 555, right here. So it'll take it, hit it at 555, and it'll kick it back to rest. You believe me? Okay, so here's my applied current. Amplitude is 25. Remember in my slide it was 110? So 25, just warning you, it may not work. Yep, didn't work. So there you can see it perturbed it, but it wasn't enough. It hit it at the base of the action potential, but it wasn't enough current. So I'm going to need to make it higher. So let's try, I don't know, we could do a batch run, but let's not. Let's just do one at a time. Okay, 50, getting closer, but I'm still not across that separatrix. So let me try 75. Nice. 75 was enough. So when I hit it with 75, it knocked it across the separatrix, and then it spins back to rest. And if I actually make it like 100 or 110 like it was in the lecture, then it just gets there quicker. Okay, we good with the unique form of bistability? Anything else you want me to do with type 2 excitability before I move to type 1? I'm in your hands. We're good? Shall I move on? Yes?
When would you change the initial value of W, or why would you do that?
Why would I do that? Well, I'll tell you what I have it set at now is I have it set so that if I don't have any current at all, the initial state is just rest. So if I change W to some crazy value, like, if I make it a lot smaller, and then I run it, it just could actually start outside the separatrix and go right to an attractor. So I chose a value for W that I know would leave me at rest. And if you were to go back to the slide, for example, so the W I chose leaves me in this little egg-shaped area. But if I change W to be really, really small, then I'm down here, and then it goes out to the oscillation. Good? All right, thanks for that question. Hearing any other questions about, if I don't have anything else about MorrisLeCar parameter set 2, I'll go to 1, the new one. So what I would like you to do is understand everything that I did in lecture 15.3. But if you're still struggling with the bifurcation diagram, don't worry, we'll come back to it. But being able to do something like what I'm about to do now would be a really valuable skill for an exam. So let's close that model and let's go into the type 1. And I've annotated my model in certain ways that I find helpful, which I'll point out to you. It's really hard to make this window bigger. I don't know why. I'm wasting a ton of time with this. But I want you to see the equations, so I'm going to continue. There we go. All right. So notice how I've annotated my model here. G calcium is 4, semicolon, type 1 uses 4.4. Actually, that should be type 2. Because I'm doing type 1 excitability. Type 2 uses 4.4. Theta W is 12. Type 2 uses theta 2. Sigma W is 17.4. Type 2 uses 30. So I've annotated my file to know where have I changed it from the other version. Because anytime you drop a semicolon in, it's just a comment. And you can also put comments within those curly brackets, functions, parameters, and so on. And I have a step pulse here. And then there's phi. Phi is 1 over 15, or 0.066666667. Type 1, it should be type 2. Okay, so what will this system do? I have set the applied current to 39. So we should be below the SNC point, right? So let's run it, see what happens. Yep, just goes to rest. I'm going to make my voltage axis something that's more pleasant. I don't know, 65 to 40, something like that. So here's a system at rest. Want to see the SNC point? So let me raise the applied current up to 39.9. Hasn't passed it yet, it's still stable. 40.05. Past the point. Now, if you want to know what the frequency is here, you can put your little marker tool on one action potential. Tells you the time. Then you can put your marker tool on the other action potential. Tells you the time. Subtract those two times, and that'll be the cycle period. You should be strenuously objecting. You said, this is you speaking. You told us that the period would emerge with an infinite period. Well, we just have to go find that point. I just showed you that from 39.9 to 40.05, which is a very small parameter change, we went from no oscillations to an oscillation whose cycle period is on the order of 1 over 0.6. It's about on the order of 1 hertz, less than 2 hertz. So remember, the MorrisLecar system starts at 7 hertz. MorrisLecar type 2 system. Now we're seeing a system at 1 hertz. But I can keep on zooming in here and trying to find this point. Add another 0. Slower yet. Add another 0. Okay, you get the point, right? I can get it to go arbitrarily slow here. Getting the point? Okay. I only really saw Max nod, but I said, Dari, he sits in for the rest of the group because it's right in front of me, so I'm looking for that nod. Do you want me to do it closer to the bifurcation point, or can I go to a higher current value? It's okay. All right. So let's go to 45. Way faster. Now what you're seeing is your motor neuron. Okay? This is kettlebell. This is laser pointer. You getting my, yeah, thank you. Okay, so that shows you the emergence of excitability through that SNC point. I could do more simulations with MorrisLecar, or I could use my ancient simulator software and show you what the phase planes look like as we pass through the SNC point. Is that it? Is that anybody interested in that? So here is my numerical software called XPP. X is for Unix. PP is phase plane. So this was written in Unix in the 1970s for doing phase plane analysis. And I've loaded it with the MorrisLecar model. And I show you the null lines. There they are. So notice that the null lines are intersecting in 3 portions. 1, 2, 3. Want to see, let's see, what's the applied current parameter? IO, okay, it's 30. So we're below the saddle point. Let's take a look at the saddle equilibrium points. So I can go singular points, mouse, click on a guess. I'm going to put it right near my saddle. Print the eigenvalues? Well, hell yeah. Draw the invariant sets? What do you think an invariant set is? It's going to be the stable and unstable manifolds. Yeah, I want those too. It didn't quite get all the way. It ran out of gas right here. But if it continued, it would connect with that point. You know what? I really want to show that to you, so I'm going to do it again. But in the upper left, can you see? There's my equilibrium points. 1 real positive and 1 real negative. Eigenvalue, one's positive real, one's negative real. That's a saddle, baby. That blue curve is one stable manifold. That blue curve is the other stable manifold. That's the unstable manifold. Ramps all the way around and connects to the rest state. That's also an unstable manifold, also a heteroclinic orbit. Let me draw those manifolds again. So I think I need to do numerics total. Instead of 120, if I do 2,000, this will work. So let's do erase, new null lines, singular points, mouse, click on the guess. Hell yeah, I want the eigenvalues. Hell yes, I want invariant sets. Oh, I chose too much time. Now it's wasting your time. But you're going to see all the sets, I promise. $2,000 was far too much. I probably only needed 200. Okay, there's one unstable manifold, and there's the other one. So now you can see it connects. Okay, so let's now stop that, and let's look at the bifurcation. So there's my null lines. Now I'll do parameter IO, and instead of using 30, I'm going to now use 40.04. So we should be past the bifurcation point. So now I'll enter it, and I'll ask for new null lines. So you see the second drawing intersects right at one point. So that's the homoclinic orbit right there. Now make it a little bit higher. Parameter, IO. Now we make it, say, 45. And now it's lifted up above. And now we have the ghost of a saddle. So you want to see what the ghost of the saddle looks like? Let's go ahead and do it. So we'll do initial conditions, and we'll do mouse. I think this should be enough. So I'll put my point here. Watch it move slowly at first and then fast, okay? This is going to happen real quick, but watch. it's gonna go real pokey. And then it's gonna get out here and then go zoom right around. And now that line tracks the top, tracks the progress of the simulation, but it's just running around the track, so you're not seeing anything new. Okay, it is 3:14. We have 6 more minutes. I can do anything with Berkeley Madonna, with this numerical XPP software. So I've set the current at 39, so it's dipped below. There are 2 intersection points here. 1, 2. So we're really close to the saddle node, but we're not there yet. Nothing? Nothing further? Yes, Marcus.
Just want to make sure the IO is the initial, but the AMP is like not.
The way I set up currents, Marcus, the way I generally work currents is like this. I usually have applied current IO bias, and then I add steps and subtract steps. It's just, for me, it's a very flexible way. I can use IO as my bias, and then I can use AMP to pop it up and pop it down wherever I want. IO doesn't go away. Whatever you set IO to, your steps are going to be added onto that, the way I've set it up. All right, if there aren't any questions, I'll go ahead and stop, but I'll stay here for a few minutes if you want to come down. But I do have to go at 3:20. Monday office hours.